You are tuned to Iri-e-learning, and I am your host, Teacher. In this structure and bonding lesson, we will explore covalent bonding involving multiple atoms. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to draw dot and cross diagrams to illustrate covalent bonding involving multiple atoms. We will start with a quick recap of 4 important points to remember. 1. Atoms bond to obtain a stable electron configuration. 2. Atoms are stable when all the shells contain their maximum number of electrons, that is, the first shell having a maximum of 2 electrons, the second and third shells holding a maximum of 8 electrons each. Thirdly, in covalent bonds, atoms acquire a stable electron configuration by sharing valence electrons. Remember, valence electrons simply means the outer shell electrons. And finally, the binding force in a covalent bond is the attraction of the nuclei for the shared electrons. Recall that nuclei is the plural of the word nucleus. So now it's time to begin drawing dot and cross diagrams to illustrate covalent bonds involving multiple atoms. The first example is carbon dioxide, chemical formula CO2. As we can see, carbon dioxide involves a covalent bond between 3 atoms, 1 carbon and 2 oxygen atoms. When a covalent compound with more than 2 atoms bond together, we must first determine the central atom to which the other atoms will bond. Generally, the central atom is the atom in the least quantity. So in this case, for carbon dioxide, carbon will become the central atom to which the 2 oxygen atoms will bond. Step 1, record the symbols and electron configurations for the atoms. We will take a quick look at the periodic table to get this information. Carbon, symbol C, is found in period 2, has 2 shells. First shell carrying a maximum of 2 electrons, the second shell carrying 4 electrons because carbon is in group 4. Therefore, the electron configuration for carbon is 2,4. Oxygen, symbol O, found in period 2, meaning it also has 2 shells. The first shell having its maximum of 2 electrons. The second shell, which is the last shell, has 6 electrons. Therefore, the electron configuration for oxygen is 2,6. We can now record the information for all the atoms involved in bonding. Note that they're all nonmetals because they have more than 3 electrons on their last shells. As a result, the 3 atoms will bond covalently. Also notice that the information for carbon atom is written in the center because it is the central atom. Step 2, draw the nucleus and the empty shells of the atoms involved in bonding with their outer shells overlapping. Note that the last shell of each oxygen atom overlaps with the last shell of the central atom, which is carbon. Step 3, fill inner lying shells with the electrons. All the atoms involved in bonding here have only 1 inner lying shell with 2 electrons each. Step 4, place bonded or shared electrons in the overlapping region, then put any remaining electrons on the shells outside of that area. Notice that there are 2 overlapping areas because the outer shell of each oxygen atom overlaps with the outer shell of the carbon, which is a central atom. When dealing with multiple atoms, we work with the atoms attached to the central atom first and then deal with the central atom last. Each oxygen atom has 6 valence electrons. Those are the number of electrons on the last shell. And of course, carbon has 4, and we will just display those right beside the information. And as we use them, they'll disappear from that point and appear on our dot and cross diagram. Now, each oxygen atom has 6 electrons on the last shell. Therefore, they need 2 more electrons to get to the stable 8 because the second shell holds a maximum of 8. Consequently, each oxygen atom will have to share 2 of its 6 electrons because it needs 2 to become stable. So there we go. Both oxygen atoms have shared 2 electrons each with carbon. After sharing 2 of the 6 electrons, you notice there are only 4 electrons remaining for each oxygen atoms, which we will put on the shell outside of the overlapping region. region. So we move now to the central atom, which is carbon, and we see that carbon has 4 electrons on the last shell. Carbon therefore needs 4 more electrons to make that stable 8 electrons on its last shell, and as a result it will have to use all 4 electrons in bonding. So let's see how it's going to divide those 4 electrons with the 2 oxygen atoms. Now the first oxygen atom shared 2 electrons with carbon, therefore carbon in turn will share 2 electrons with the first oxygen. And the same happens with the second oxygen, which shared 2 electrons with carbon, therefore carbon will share 2 electrons with the second oxygen. So if you notice, we have used all our valence electrons at this point in time. There are none remaining. Step 5, count to ensure that the last shell of each atom involved in covalent bonding contains their maximum number of electrons. And remember, we don't have to count the inner lying shells because they already contain their maximum number of electrons. However, it is important to remember that the bonded electrons are counted for the atoms that share them. So the first oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons on its last shell, giving it a stable electron configuration of 2, 8. The second oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons on the last shell, so it now has a stable electron configuration of 2, 8. Finally, carbon has 1, 2, 3, 4, 5, 6, 7, 8. Carbon now has a stable electron configuration of 2, 8. So all the atoms now have stable electron configurations, so we know our dot and cross diagrams were accurately done. Step 6, represent the covalent bond as a stick diagram. So we're going to write the symbols of the 3 atoms, oxygen, carbon, oxygen, written in the order in which they bonded in the dot and cross diagram, leaving sufficient space between the atoms to draw the number of covalent bonds that exist between them. So how many pairs of electrons are shared between the first oxygen and the central atom carbon? If you said 2, then you are correct. So we have a double bond drawn between the first oxygen and carbon. Between the second oxygen and carbon, we also have 2 pairs of shared electrons, and so there's also another double bond formed there. Therefore, we can say that carbon dioxide is a covalent compound in which the carbon forms a double bond with each oxygen atom. To complete this example, this is what our dot and cross diagram would look like if we chose to draw it without the inner lying shells with electrons. Next is water, H2O, another example of a covalent compound consisting of more than 2 atoms bonding together. Water consists of 1 oxygen atom binding with 2 hydrogen atoms. Therefore, oxygen will be the central atom to which the hydrogens will bond. Step 1, record the symbols and the electron configurations of the atoms. We already obtained this information from previous examples done with these atoms. So the hydrogen atoms have 1 electron each on the first shell, and oxygen has 2 shells with 6 electrons on the last shell. Step 2, we're going to draw the nucleus and the empty shells of all the atoms involved in bonding, and of course having their outer shells overlapping. Here we see that oxygen is a central atom to which both hydrogen atoms are bonding. Step 3, we're going to fill the inner lying shells with their electrons. The hydrogen atoms do not have inner lying shells, so as a result, it's only oxygen. Oxygen has 1 inner lying shell which carries 2 electrons. Step 4, place bonded or shared electrons in the regions of overlap and then put any remaining electrons on the area of the shell outside of that region. Note that the hydrogen atoms have 1 shell with 1 electron each, and the oxygen has 2 shells, the first shell having 2 electrons and the second shell carrying 6 electrons. And so we will display the number of valence electrons that each atom has. Those are the number of electrons on the last shell. Hydrogen has 1 electron, and seeing it's only a first shell, it holds a maximum of up to 2 electrons. So as a result, hydrogen needs 1 more electron to become stable, and therefore it will use its 1 electron in bonding or in sharing. After sharing 1 electron, hydrogen has no more electrons to place on the area outside of the overlapping region. The same applies to the second hydrogen, it shares one electron. And of course, after sharing its one electron, there are no more electrons remaining to be placed outside of the overlapping region on that shell. Now we're on to the central atom, the oxygen. Oxygen has 6 electrons on the last shell. Since the first hydrogen shared one electron with oxygen, oxygen will share back one electron with hydrogen. The same happens with the second hydrogen. It shared one electron with oxygen, so oxygen will share one electron with hydrogen. As a result, oxygen now has 4 electrons remaining, and these 4 electrons we place on the shell outside of the overlapping region. Step 5, this is where we're going to count to make sure all the atoms have the maximum number of electrons on their last shell. So hydrogen, having only one shell, has a maximum of 2 electrons now, so it now has an electron configuration of 2. The same happens with the second hydrogen. Its first shell now has 2 electrons, so its new or stable electron configuration is 2. For oxygen, 1, 2, 3, 4, 5, 6, 7, 8 electrons, so oxygen now has a stable electron configuration of 2, 8. Step 6, this is where we're going to draw the stick diagram to represent our covalent bond. And so we'll write out the atoms as they have bonded in the dot and cross diagram. So we have hydrogen followed by oxygen followed by hydrogen. We leave sufficient space to insert the lines to represent the number of covalent bonds. So for the bond formed between the first hydrogen and the oxygen, note that there is one pair of shared electrons. So we have a single covalent bond or a single bond. For the second hydrogen and the oxygen, we notice there is also one pair of electrons, so we have another single bond being formed. As a result, a molecule of water is oxygen, forming single bonds to each hydrogen atom. To complete this example, this is what our dot and cross diagram would look like if we chose to draw it without the inner lying shells with electrons. The final example is hydrogen cyanide, HCN. Now, it's a little difficult to identify which atom would serve as a central atom because there's one hydrogen, one carbon, one nitrogen. The quantity of all the atoms are the same. In such a case, we use the central atom in the formula as the central atom for the dot and cross diagram. As a result, carbon becomes the central atom for hydrogen cyanide. We record the information for each atom involved in bonding. Hydrogen H has one shell with one electron. Carbon C has 2 shells with 4 electrons on the last shell. Nitrogen N has 2 shells with 5 electrons on the last shell. Next, we shall draw the atoms with empty shells, ensuring that the last shell of the central atom overlaps with the last shells of the other 2 atoms. Notice that only carbon and nitrogen contain inner lying shells, the first shells that hold a maximum of 2 electrons each. Now it's time to show how the atoms bond. So we display the valence electrons for each atom below their information. Keep in mind that the valence electrons are the electrons on the last shell of the atom. Hydrogen has 1 valence electron, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. So hydrogen has 1 electron and it has 1 shell. We know from the electron configuration rules that the first shell holds a maximum of 2 electrons. Therefore, hydrogen needs 1 more electron to become stable, and as a result, will have to use its 1 electron in bonding. Then we go to the next atom, which is the nitrogen that's attached to our central atom. Nitrogen has 5 electrons on the last shell. We know that last shell is the second shell, therefore, it will need 3 more electrons in order to make the maximum of 8. So nitrogen will share 3 of its 5 electrons with carbon. After sharing 3 of its 5 electrons, nitrogen has 2 electrons remaining, which are placed on the shell outside of the overlapping region. Now, after hydrogen has shared 1 electron with carbon, carbon will share back 1 of its 4 electrons with hydrogen. There are 3 electrons remaining for carbon, and since nitrogen shared 3 electrons with carbon, carbon, then carbon will share back 3 electrons with nitrogen. So all the valence electrons have been used up in the dot and cross diagram. Therefore, we have an idea that our illustration was done accurately. However, it is always good to practice counting the number of valence electrons after bonding to ensure that the valence shell of all the atoms contain the maximum number of electrons. Starting with hydrogen, hydrogen has one shell which holds a maximum of 2 electrons, and as we can see, hydrogen now has 2 electrons, giving it a stable electron configuration of 2. Next, we count the electrons on nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has a maximum of 8 electrons on its last shell now, giving it a stable electron configuration of 2, 8. Then to the central atom, carbon, 1, 2, 3, 4, 5, 6, 7, 8. The central carbon also has a maximum of 8 electrons on its last shell, therefore has a stable electron configuration of 2, 8. Finally, we can represent the covalent bond as a stick diagram, so we record the symbols of the elements involved in bonding in the order in which they bonded in the dot and cross diagram. Hydrogen, carbon, nitrogen. Make sure to leave sufficient space between the symbols to insert the number of covalent bonds formed between the atoms. Between hydrogen and carbon, there is one pair of shared electrons, which resulted in a single bond. Between carbon and nitrogen, there are 3 pairs of shared electrons, which resulted in the formation of the triple bond. Therefore, we can complete this example by showing what the dot and cross diagram would look like without the inner lying shells. Here are the lesson summary points. Atoms bond to obtain a stable electron configuration. Covalent bonds are formed between nonmetal atoms only. Covalent bonding involves nonmetal atoms sharing valence electrons. The atoms involved in covalent bonds will only share the number of electrons needed to become stable. A pair of shared electrons is called a covalent bond. Covalent bonds are either single, double, or triple. The binding force in the covalent bond is the attraction of the nuclei for the shared electrons. The central atom in a covalent bond with multiple atoms is typically the atom in the least quantity. It's quiz time, and you have 5 seconds to answer each question after it is read aloud. Question 1. Carbon has 4 electrons on the last shell, and hydrogen has 1 electron on its first and only shell. How many hydrogen atoms would be needed to form a covalent compound with carbon? The answer is 4 hydrogens would be needed to form a compound with carbon. Question 2. Which statement is incorrect about covalent bonds? A. A covalent bond is formed between nonmetal atoms only. B. A covalent bond is formed between a metal and nonmetal atom. C. A covalent bond is formed when atoms share valence electrons. D. Atoms in a covalent bond will only share the number of electrons needed to become stable. The answer is B, where the incorrect statement about covalent bonds is that covalent bonds are formed between metals and nonmetals. We know that covalent bonds are formed between nonmetal atoms only. Question 3. How many covalent bonds occur between the carbon and nitrogen in the covalent compound shown in the diagram below? A1, B2, C3, D4. The answer is 3, because there are 3 pairs of electrons, hence 3 covalent bonds occur between carbon and nitrogen. Question 4. Identify the diagram that accurately represents the covalent compound ammonia, which is formed between nitrogen, which has the electron configuration 2,5, and hydrogen with electron configuration of 1. The answer is B, NH3, where 3 hydrogens are connected to 1 nitrogen. Notice that nitrogen needs to share 3, but hydrogen will only share 1 with it, so we'll need 3 hydrogens to share with the nitrogen in order for nitrogen to end up sharing a total of 3 electrons. Question 5. Water is a covalent compound formed between hydrogen, which has the electron configuration of 1, and oxygen, which has the electron configuration of 2,6. Which diagram correctly represents the covalent bond in water? The answer is B, because 1, oxygen would be the central atom to which the hydrogens are attached, and 2, after sharing 2 electrons, 1 electron with each hydrogen, oxygen would have a total of 4 electrons remaining, which are placed outside of the overlapping region on that last shell. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.